In the last video, I mentioned 5 different ways to visualize a complex function, and we are going to use them to visualize some common functions in this video, and along the way, we identify some features of them. Of course, we aren't using all 5 ways, but only the most interesting or informative ones for each function. Even for something simple like this sort of function, it can still be pretty interesting. The most informative method of visualization in this case is the ZW plane. As always, the Z-plane looks like this. Let's say the complex constant c is here, with the corresponding vector. Then it turns out that the adding constant function is just a translation by this vector. It isn't particularly difficult to see why either. Using the geometric intuition of adding up 2 complex numbers by vector addition in a previous video, we know that in order to go from z1 to the sum, we simply translate by the vector z2. So addition by a constant is really just a translation of the whole plane, so ZW plane clearly illustrates what the function is doing, but also kind of boring. What's more interesting is how the Riemann sphere method does the visualization. More specifically, how would the function of adding 1 look like on the Riemann sphere? Well, here we go. One thing to note is that this point where the yellow curves congregate is 1, because it was originally at the south pole, which corresponds to 0. But there are some other features to notice as well, including another special point, the North Pole, because the North Pole stays exactly where it was throughout. The other thing to notice is that these white and yellow curves are still circles and still intersecting at right angles. You can figure out why after the next video about Möbius maps. Similar to the previous adding constant function, we are using ZW plane visualization. Like before, we first imagine a grid, choosing a random point to be the complex constant, and here we go. This time, it is a combination of stretching and rotation, and we can see why pretty easily. If we write c and z in their polar forms, then the result looks somewhat like this. And notice that the modulus changes by a factor of little r, which corresponds to a stretching, and the argument increases by little theta, which corresponds to a rotation. So every complex number is stretched and rotated by the same constant amount. But there is one more observation to make. Can you see it? This is a linear map. Why? As I said in a Jacobian video, a linear map is where parallel lines stay parallel, and yes, the lines are parallel here. Do the lines still have even spacings? Well, yes, the spacings between the parallel lines are still the same. Is the origin fixed? Well, let's play back in reverse. Yes, the red dot in the middle stays fixed, so this is a linear map. But for any linear map, there is a corresponding matrix which looks like this. The difference here is that 1, 0 represents 1 on the complex plane, and 0, 1 represents I instead. To construct the matrix, we first write C as A plus BI. Then under multiplication by C, 1 is mapped to C, so the first column of the matrix is AB. Now where does I go? Well, under multiplication by C, it is mapped to negative B plus AI, so the second column is negative BA. So the multiplying by constant function is a linear map corresponding to a matrix of this form, and that means we can correspond a complex number to a matrix. This is not the only connection. The addition of complex numbers is exactly the same as addition of matrices, and we can see the same thing for multiplication, which is already quite surprising, And if you know something about matrix exponentiation, complex number exponentiation is the same as the corresponding matrix one. So there is virtually no difference between the two here. In fact, if you really can't accept that something squares to -1, then just look at the corresponding matrix expression here. We are only calling this I for simplicity, and this matrix -1 because it behaves like -1. But the most important reason I bring this up is that it will be useful in developing intuition for complex differentiation in a future video. First off, we will be using, again, the ZW plane method for exponentiation. The transformation itself might look complicated, but what matters is the result, because there are lots of choices for the transformation. The most important takeaway here is that while the Z-plane is a rectangular grid, the W-plane is a polar grid. So the nature of exponentiation is to turn something rectangular to polar. More specifically, the image of a vertical line is a circle centered at the origin. You can imagine that the line wrapped around it, in fact, infinitely many times. What about horizontal lines? This time, its image is just a ray emanating from the origin. So under exponentiation, a rectangle becomes an annular sector. The explanation for all these is that if we write z as x plus iy, then its exponential looks like this. X, the real part, controls the modulus, and y, the imaginary part, controls the argument. On a vertical line, the real part is unchanged, and so the modulus of the output is unchanged, which means the output has to be a circle centered at the origin. In a similar vein, a horizontal line has the imaginary part fixed, so this time the argument is unchanged and the output would be a ray from the origin. This theme is going to be more prominent when we switch to using domain coloring for visualization. The first thing to see is the horizontal color bands, because again, the imaginary part, and thus argument, stays fixed along the horizontal lines, because the hue corresponds to the argument. At the same time, the modulus is represented by lightness, and so the lightness increases as we move to the right. And along vertical lines, only the argument changes, so the hue changes periodically along them. The Riemann sphere visualization of the exponential is quite interesting as well, though not necessarily illuminating. Let's take a look. The transformation is quite complicated, but there are a couple of things to notice. Again, the yellow curves congregate at 1, because that's e to the power 0. The other thing is to notice where points near the North Pole go. You can see that it goes everywhere. It is quite chaotic, and that's because infinity is what's called an essential singularity of the exponential function, but we are getting way ahead of ourselves here. However, the image can be made less chaotic. If we instead project a rectangular grid onto the sphere, forming an alternative grid structure, then the grid becomes latitudes and longitudes, just that the latitudes don't spread evenly. So these are the different ways of visualizing exponentiation. For the power function, domain coloring is probably the clearest, but all others are useful in some specific situations. Let's take a look at the domain coloring plots for z, z squared, and z cubed respectively. Can you see any pattern here? Pause the video if you want a bit more time. If you circle around the origin, the hue goes around once, but also note that it goes from red to green to blue anti-clockwise. For the squaring function, if you circle around the origin again, the hue goes around twice, again in the same anti-clockwise configuration. For the cubing function, the hue goes around 3 times, again from red to green to blue. For negative integers, here are the domain coloring plots, but this time, if we want to go from red to green to blue, we have to go clockwise instead. So you can think that the hue goes around -1 times. For 1 over z squared, similarly the hue goes around -2 times, and the plot for 1 over z cubed sees the hue going around -3 times. So in general, for n being an integer, the hue goes around the origin n times. But why? If we write z in its polar form, then z to the n is this, and notice that the argument is now n times the original. So the corresponding hue goes n times as quickly as theta, like this. So the hue goes around n times. That's what the domain coloring plots tell us. An interesting method is vector fields, but here I am using Polya vector field since it is useful in later videos. For instance, this is the identity function, and you might notice there are 4 regions of flow separated by some invisible walls. Now, what about z squared? The Polya vector field looks like this, and this time we have 6 regions of flow. Maybe you have spotted a pattern here. Let's go to z cubed. You might have guessed it, there are 8 regions of flow here, and in general, if n is a positive integer, the plane is divided into 2 n+1 regions. What about when the exponent is negative? Well, the reciprocal of z looks like a source pumping out fluids, but it's better to think of it as an electric field generated by a positive charge, called a monopole. Now decrease the exponent to -2, and then we would get this vector field. Physicists might recognize this as the electric field generated by a dipole, a positive and a negative charge put together. Now think about what happens when the exponent goes to -3. Just take a look. This time, we have 2 opposite dipoles stuck together, which is called a quadrupole. Normally, I would end the set of examples here, but the next case, z to the -4, is kind of surprising. The vector field is the electric field generated by 2 opposite quadruples, which is, not too surprisingly, named octupole. However, because there are 6 loops, it kind of messes with my brain. But indeed, this is true, an octupole with 6 loops. All these Polya vector fields are pretty interesting, and we are going to explore a little bit more in a future video about Laurent series. I'm sorry if I butchered the French pronunciation. I would be remiss if I don't tell you where this picture for the ZW plane comes from. It turns out it is the function 1 over z. Again, we start off with the grid, and here we go. The result is beautiful, but what's more, all these are circles or lines passing through the origin, and they still intersect at right angles. But here is a meta question. The original grid can be thought of as the function returning z itself, but how did I smoothly transition from z to 1 over z? One possible choice is to let the exponent go from 1 to -1 smoothly, but this instead would be the transformation. So what did I do? The transformation I did was quite complicated. Here, theta changes from 0 to pi. But how did I come up with this? It has something to do with the next method of visualization. The reciprocal function is best illustrated with the Riemann sphere, because the Riemann sphere just undergoes a simple 180-degree rotation about the x-axis. If instead of rotating by pi, we rotate by angle theta, then this is the corresponding function. This type of function is called a Möbius map, something that we will deal with in the next video. So far, we have dealt with functions where the power is an integer, but what about nth roots? Things are quite different. But first, we revisit domain coloring plots a few minutes ago. The hue goes around the origin n times for z to the n, so a natural generalization would be that it goes around c times in z to the c as long as c is real, whether it is an integer or not. Let's consider the case where c is a half and imagine what the domain coloring plot looks like. Let's say this point is colored green. When we go around the origin, what will happen? Well, let's magnify that point so that we can see clearly, and also we put up this hue spectrum. Originally, we are at the top here, but as we go around the origin, the hue goes only half as quickly, so let's see. The issue here is that originally this point is supposed to be colored green, but somehow you are supposed to color it magenta? So which color? How about none? We just removed this problematic point from consideration, but other points remain unchanged, so points slightly above the problem point are green, and points slightly below it are magenta, and points opposite it are then blue, or more precisely, azure. However, this is just an arbitrary cycle around zero. All cycles, large and small, would have to have a problematic point somewhere as well, depending on where we start the cycle. Now it makes sense to choose the starting points all in the same direction, and the line that these points form is called a branch cut. However, the usual convention in this case is that the branch cut is the negative real axis, and this is the domain coloring plot. One thing to note is that while the branch cut is somewhat arbitrary, it has to start from the origin, because we are always circling around the origin, and because the circle can get as small as we want, the problematic points extend all the way to the origin as well. For this reason, the origin is called a branch point. This branch point is not arbitrary, it is a point intrinsic to the function itself. Think about it this way. The purpose of the branch cut is to prevent us from encircling the branch point completely, so it could be any curve from 0. But what is a branch? Let's take a step back and focus on what this function really is. More concretely, what if z equals 9? We assume that 9 is not on the branch cut. In this case, there are two possible answers, namely 3 and -3, because both square to 9. Let's choose 3 for the time being, which corresponds to a light red dot. It could have also been -3 corresponding to a light cyan dot, because red and cyan are opposite colors on the color wheel. Now think about the points nearby 9. What should be their color? The square root of this point is either very close to 3 or very close to -3, which means it should either be colored slightly different shade of red or slightly different shade of cyan, but it makes more sense to color it light red, simply because it is so close to a red dot. Similarly, you can make a choice for the other neighboring points. Again, if you have chosen any color to be cyan, the color change would be too abrupt, something that we don't want. So what we said before was just that this process of choosing colors could not be done throughout the complex plane. The branch cut is where the colors would abruptly change. But apart from the cut and the branch point, everything's alright. That's the most we can do. The corresponding function is called a branch of the square root. But notice that I say a branch, because this is also a branch, To specify which branch you are talking about, you have to state where the branch cut is and the function value at least one point. But there is another approach to all these. Given the two choices, what if we don't choose and say that the square root is both 3 and -3? Of course, we can't simultaneously color a point red and cyan, but we can use 3D plots to plot 2 points simultaneously, like this. More specifically, they have coordinates 9, 0, 3 and 9, 0, -3 respectively, and we can consider the resulting Re-im plot, which is quite an interesting plot. There is no branch cut here anymore, just that because it is a Re-im plot, along this line, the real part of the square root is 0, and so the 2 points to be plotted are at the same location. And here is the obligatory rotation of this plot. But actually, this plot isn't something strange if somehow we have 4D vision. What do I mean? Let's take a look at the real version. Usually, this is how we would plot the graph of square root of x, but with the spirit of including both square roots, let's plot the -1 as well. This isn't something crazy, this is just a parabola. If we rotate the plot by a right angle, then we get the plot of a simple function, the squaring function. Rotation is not the only choice though, because a reflection across this diagonal line y equals x also works. So it seems reasonable that if we do a 4D reflection or rotation on this plot, we would get the Re-im plot for the squaring function. Let's do that. This is indeed the plot for the squaring function. So if we have a 4D vision, these two plots represent the same thing, just viewed from different perspectives. We still have another function to talk about, logarithm. Remember that the exponential function turns rectangular things to polar, so quite naturally you would expect that logarithm does the opposite, turning polar things rectangular. But there is a catch here, which is quite similar to square roots. Just like the previous case, we can ask what is the logarithm of 1. Normally, the answer is just 0, but it could also be any multiple of 2 pi I because when you take e to the 2 pi I, it still gives 1. In a sense, it is worse than the square root because there is an infinite number of answers. As before, we first consider what the domain coloring plot would look like, but this time we go through a bit more quickly. In our case, let's choose the answer 0 because that's the usual convention, which actually corresponds to the color black. 2 pi I corresponds to a green color, while -2 pi I corresponds to a purple color. And since we choose the black color for 1, points very close to 1 would also be of very dark color. Of course, just like 1 itself, you could have also chosen a slightly different shade of green or a slightly different shade of purple, but we don't want these abrupt changes. If we make the sensible choice for each point based on its neighbors, this is the result. And again, you can see the abrupt change in color near the branch cut, which is conventionally taken to be the negative real axis. And the branch cut extends all the way to the branch point at 0 as well. This formula is the reason we have to have a branch cut somewhere. When we cycle around 0 counterclockwise, theta always increases. If you start with theta being -pi, after a cycle, it will increase to +pi. So there has to be a jump for every cycle, hence the branch cut. But before the finale, where we consider all these to be the logarithm of 1, let's take a look at some of the other ways to visualize logarithm. First, we have the ZW plane method for the conventional branch of logarithm. As we expected, the polar grid turns into a rectangular one, but note that the result is trapped between two horizontal lines, which are at height plus and minus pi respectively. This part is supposed to be filled, but the grid lines would be too dense to see anyway. The logarithm does not act naturally on rectangular things, but the transformation is interesting nonetheless. Let's see. Well, again, the resulting grids are trapped between the two horizontal lines, and this part is supposed to be filled in as well, just that the grids are too dense. So this ends the journey of the ZW plane method. What about the Riemann sphere visualization? The transformation is also quite interesting. As always, this is our starting point, and here we go. One thing to note is that these curves are actually circles or circular arcs. The explanation for this could be deduced from the next video. In this case, these circular cavities aren't because the curves are too dense, they actually correspond to the horizontal lines like before. Alright, I think we should start the finale, the 3D plot visualization of logarithm. As said before, the logarithm of 1 has infinitely many answers, and this time we just take all of them. But instead of reimplot, we use the imreplot for logarithm instead. So we are going to plot the points 1, 0, 0, 1, 0, 2 pi, 1, 0, negative 2 pi, and so on, which correspond to 0, 2 pi I, and negative 2 pi I respectively. And this is the 3D plot, which looks like some spiral staircase. But what's more is that we can also demystify this 3D plot by doing some 4D reflections to it. Here it is. And there isn't any peculiar branch things in this plot, because this is a plot of a perfectly nice function, the exponential function. So again, these two plots are the same if we view them from different 4D perspectives. And that's it. Which plot or method of visualization do you like the most? Leave a comment down below. Before you really go, please watch this video about problem of Apollonius because it will be relevant in the next video about Möbius maps. If you like this type of content, please do consider supporting this channel via merch like mugs or hoodies, or Patreon, where you can see videos at least 24 hours in advance. As always, thanks for these patrons and subscribe with notifications on. Like the video, share and comment as well. I'll see you next time. Bye!